With fluids, there's kind of one equation to rule them all, and it's Bernoulli's equation. Here's Bernoulli's equation. We're going to look at a few situations and wrestle with what this is. So it says P, that's pressure, pressure 1 plus rho GH1 plus 1/2 rho V squared 1 equals P2 rho GH2 1/2 rho V2 squared. So let's draw an illustration of what we're talking about here. Okay, let's look at this here. There's a pipe of water that's taking water from this tank over here. And when it enters the pipe, the water is going to move with a speed of 10 meters per second. And there's a drop in height there. So as the water drops, what's going to happen is it's going to go faster along here. And the pipe comes out and the water shoots out the end of the pipe there. So we can calculate with Bernoulli's equation what the speed of water is going to be at the end of the pipe there. So to calculate the speed over here, we're going to use Bernoulli's equation. Now, the first thing to say is about pressure, this P1 and P2. Now this side of the water is exposed to the air, and that side of the water is also exposed to the air. So the pressure on this side is going to be atmospheric pressure P0. And the pressure on this side is also going to be atmospheric pressure P0. So there's no pressure differential in this case because they're exposed to the air. Whenever water is connected to the air, it's going to be in equilibrium pressure to that air. So we can say that the pressure here is equal to the pressure there. And we can cancel it from the two sides of the equation. And then we can also say that this H1 and this H2, that's like the difference in height. So if I think about that, the delta H there is H1 minus H2. H1, H2. So I'm going to put these two terms together. So we get rho G, H1 minus H2, plus 1/2 rho V1 squared equals 1/2 rho V2 squared. So again, this is the height differential. And you can see that all these terms actually have rho as part of them. So we can already cancel out the rho term. Okay, there it is. I can solve this equation for V2. I get this here, square root 2g delta H plus V1 squared. So we can plug in numbers to calculate what the velocity is going to be. We get square root 2 times 10 times 1.5. 1.5, that's the height differential, plus 10 squared. We get square root 400, so the velocity is going to be 20 meters per second. Ba-bam! So what's going on here is that as the height drops, the water gains more speed. And there's no pressure differential because of the atmosphere. Let's do another example. The best way for you to improve your grade is with a practice test. On my site, there are some free practice tests. Click the link below to get yours. Okay, let's imagine there's a pipe where it's a skinny pipe and it opens up into a big, fatter pipe. So there's going to be a different cross-sectional area. Let's give it a radius for each one. And we can say that the water in the beginning of the pipe is under a certain pressure. Let's say it's 1 atmosphere. Okay, so we're going to think about what the speed of the water and the pressure of the water is going to be in the fat part over there. And we're going to need to use Bernoulli's equation. So let's think a little bit about what's going on here. Firstly, there's no height differential. So the pipe, the skinny part of the pipe and the fat part are at the same height. So this term and this term in Bernoulli's equations are going to be equal to each other and they're going to cancel out. Secondly, there is going to be a pressure difference. So this part of the pipe and that part of the pipe will not be under the same pressure. I didn't say that they were both connected to atmosphere or something. This is just a pipe going in this far. We don't know what's going to happen. Maybe there's, I don't know, something on the end. It doesn't matter. But we didn't say the pressure is an atmosphere there, like we did in the last one. So we have to calculate what the pressure is going to be there. Now, we can actually use the flow concept from the last one to calculate what the velocity is going to be. So we're going to begin there before we use Bernoulli's equation. The flow rate says the cross-sectional area times velocity is going to be same. That is, the flow of water here is equal to the flow of water there, but they're going to have different speeds. So we can calculate what V2 is going to be. So we get the area 1 divided by area 2 times velocity 1. That's going to be V2. Okay, plug all the numbers in, and what do we get? So the speed over here is going to be 1.1 meters per second, or 10 over 9 meters per second. So now we can use Bernoulli's equation and figure out what the pressure is going to be here. So let's write down Bernoulli's equation again. So what do we say? The first thing we can say is the heights are the same, so these two terms will cancel. So we can calculate pressure 2 already. It's going to be this left side minus that term there. So pressure in the second part will be P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared. So we can put in all our numbers. So we get 100,000 plus 1/2 times 1,000 times 10 squared minus 1/2 times 1,000 times 1.1 squared. So we get that the pressure is 149,000 pascals. So the pressure over here is actually going to be higher. So the speed here is faster and it slows down over here. But to compensate for that slower speed, it actually increases the pressure. So the pressure here is going to be higher than the pressure over there. That's Bernoulli's formula. We need to do some more examples to really understand this. Was that clear? Or do you have any questions about Bernoulli's formula? If there's anything that you're wondering about this, write it in the comments below. I read every single comment and answer them all. The best way for you to improve your grade is with a practice test. On my site, there are some free practice tests. Click the link below to get yours.